Thank you for inviting me, and thanks to the organizers for the past week, which was very nice, and I'm sure also this week will be. So last week we saw two lectures in particular, the ones by Lotte and the ones by Marcus. And Lotte kind of explained how WKB approximations and these coordinates that were called X gamma appeared in the context of supersymmetric field theories. And the thing is that this approach through WKB approximation can be abstracted and generalized quite broadly. And today I'm gonna tell you how an alternative approach to study these coordinates X gamma, which is based on this abstraction plus some input from discrete integrable systems. I will try, at least in the beginning, to keep kind of two sides of the blackboard. On this side, I'll keep the general formulation, and here I'll have a running example that I think it's always useful. So I will start with some kind of general picture. And then I will discuss BPS spectra of 5-dimensional theories. And then I will show how to solve what is called the BPS Riemann-Hilbert problem. So the thing that we should start from is kind of the abstraction of what it means to study BPS states. So this can be vary depending on what string theory realization you're considering, and concretely they might be realized in different ways. But the kind of minimal set of requirements is encoded in what is called the BPS structure. And this is given by several ingredients. So it's kind of a list. It's a mathematical definition. And the first thing that we need is a finite rank free abelian group gamma. So a lattice. We have a lattice gamma. What is this lattice? Of course, this sounds, very highbrow, but in the end, we have particles. So these particles will be characterized by their conserved charges. So the elements of this lattice are just the quantum numbers of these particles. Now, the pictures that I'll have in mind will be that of geometric engineering. So in this context, we have M theory on a Calabi-Yau threefold. And then if we think of it in terms of type 2A description for simplicity, these BPS particles will be D0, D2, and D4 branes wrapping compact holomorphic cycles on this Calabi-Yau threefold that I'll denote by X. There's no D6 branes because I'll only consider non-compact Calabi-Yau. So we have, why do these correspond to particles? Well, we have our Calabi-Yau threefold X here, and then we want to study our physics on R4 times S1. S1 is the M theory circle. Now, if you look at things that can produce BPS particle here, well, you can have either the zero branes that are just localized at a point here, and here they will have their word line, or you could have the two branes that are wrapping two cycles in the Calabi-Yau geometry, compact two cycles in the Calabi-Yau geometry, so the remaining dimension is still a word line, or again, D4 branes that are wrapping compact four cycles in the geometry. And then the quantum numbers, the conserved charges of the particles in this geometric realization are just the so are given by this lattice, which is just a cohomology group of this Calabi-Yau threefold. So you have a cohomology with compact support, and I'm describing them in terms of cohomology. Physically, you should think about the gauge field that lives on the D brane. So you should consider sheaf cohomology here, because if we want to describe gauge fields localized on subspaces, we should really use the language of sheaf theory. So this is our lattice. It's even dimensional cohomology of some Calabi-Yau threefold. Then the second requirement, the second thing that enters in the description of BPS particles is a skew symmetric form from gamma to Z. Yes, please. So as I said, I'm considering cohomology with compact support. The idea is that you're really considering the vector of Chern classes of sheaves that are compactly supported on these cycles. Yes, yes, but it's because it's compact support, they're dual really. But I would prefer to think about it in terms of cohomology. But in this context, it's really equivalent. So the second ingredient is the skew symmetric form. And the skew symmetric form physically is what is known as the Dirac pairing. So due to Dirac quantization, if you have an electric and magnetic charge, then you have this, which is in Z. But if you have a conserved charge, because this only sees electric and magnetic charges, if you have a conserved charge that is related to a global symmetry, then this is zero. This is what we call a flavor charge, and it's in the radical of this pairing. So we have this skew symmetric form, which is just the Dirac pairing physically, and mathematically is the antisymmetrized Euler pairing between sheaves. This it was also discussed last week in the context of quivers by Marcus. The third thing that we need, well, we are talking about BPS particle, right? So what we need is a central charge. So a central charge is a group homomorphism Z from this lattice to C. And, well, it associates to an element gamma, its central charge Z gamma. And as we probably all know, hopefully, the BPS bound is just that the modulus of the central charge is the mass of the particle. Also, the phase is important, actually, but I don't want to enter in that. But we really need the full complex central charge. That's important. And finally, we have a map of sets. Omega from gamma to, let's say, Q. And this is Donaldson-Thomas invariant BPS invariants that were also introduced last week, both by Marcus and by Lotte. So this is kind of a, shopping list. What we want in order to describe BPS states. And so what we really want to study is, okay, we have these BPS states. We want to see in a given point in the moduli space of the theory, in the moduli space of this Calabi-Yau, what are the ones that are stable, really, that appear in the as stable particles that do not decay. And the ones that are stable are the ones with omega different than 0. Because this is, we saw it last week, this is kind of an index. So if it's a BPS representation, omega will be different than 0 if it's stable at that point. So array Z gamma in C, so you consider the complex plane of central charges. These are complex valued. And array is called active if omega is different than 0. So if omega of gamma is different than 0. And these will be the stable particles. So the order 0 problem, which is already quite a complex problem, is I give you a Calabi-Yau threefold. I give you a point in the moduli space of this Calabi-Yau threefold. What are all, can I list all the stable particles? Now, normally one would compute a generating function for these invariants, and that's already very, very good. But there are cases, for example, Lotte last week wrote down explicitly the BPS spectrum of SU2 super Yang-Mills in 4D. So she wrote, okay, we have a strong coupling chamber. This is the spectrum, monopole and dione. Good, it's there. And of course, you can write a generating function, but this is, if you want even a stronger statement, I can just write them down in closed form. And I have another chamber in which I have this infinite number of BPS states, the weakly coupled chamber. So the first thing that I want to see is a statement like that, but for 5-dimensional theories, which are typically more complicated. Because the 4-dimensional theories in this context come kind of by degenerating this description from M theory to type 2A. The second problem that I want to solve is this BPS Riemann-Hilbert problem. And this, as far as I know, was first considered by GMN, Gaiotto Mornaitsky in 2010. But today I will discuss a formulation due to Bridgeland from 2021. But a bit of a simplified version of that, which will be sufficient for the things that I'm going to discuss today. So this BPS Riemann-Hilbert problem is about finding these very important functions x gamma that Lotte talked about last week. So remember, to find them, she introduced this notion of spectral network. It was a very computationally intensive task. You have to go and plot all these trajectories of differentials, and in this 5D case, it's even more messy. So if we can avoid that, we're happy. So the statement of this is that we want to find a piecewise holomorphic map X, which is from C star in epsilon, like the epsilon of the WKB approximation in the context of spectral networks. But if you want, if you don't know anything about spectral network, we just introduce a formal parameter epsilon. It has some geometric meaning that I'm not discussing now. From another C star to the rank of gamma. So a rank of gamma copies of C star. And this will associate to epsilon function x gamma of epsilon. And such that, so if you start varying either epsilon or your moduli or some parameter in such a way that the ray of epsilon crosses an active ray. So if epsilon crosses an active ray L gamma counterclockwise, then we have, so let's say that you have kind of one of these rays, L gamma, and you're going counterclockwise. So here you have above and below. I'll denote it by epsilon plus and epsilon minus. You will have that x gamma of epsilon plus will be equal to x gamma of epsilon minus times a product over all the states whose central charges lie on this ray of some ugly looking expression, but that is actually not that ugly, that involves this omega gamma, the pairing, and these other x gamma. And this is called the Kontsevich-Soibelman formula, let's say. And we also want to fix that as epsilon goes to 0, x gamma goes as the exp of z gamma over epsilon. So this is kind of our asymptotic behavior of the Riemann-Hilbert problem. So this is all kind of very abstract, but if you remember, if you start from this WKB approximation, you kind of find this jump formula, but this is actually a very general formula. So in the end, what we want to find is try to see if this behavior can just allow us to completely fix these x gamma instead of going in some other roundabout way. Sorry? Yes, absolutely, sorry. So this sign depends on what is this omega gamma prime. So this sigma gamma prime is fixed by this omega gamma prime. For us, we will only need the fact that for omega of gamma is equal to 1, then sigma is -1. That's it. Otherwise, you have to start thinking about twisted tori and things like that, but that would bring me too much into this thing. We will only need this. Here, counterclockwise. Yeah. And the product lies over all the, here there might be more than one central charge that lies on this ray, and you have to take the product of over all of them. Yes. So that's the thing. If you think about a usual Riemann-Hilbert problem, like for example a matrix-valued Riemann-Hilbert problem, for example, if you start with an ODE, you have two perspectives. Either you start from the ODE and you compute the monodromy. This is kind of the direct Riemann-Hilbert map, or you give the monodromies as input, And then you solve the ODE given this. And this is the inverse Riemann-Hilbert map. And typically this is what is meant by Riemann-Hilbert problem. This is the same perspective. So to determine this Riemann-Hilbert problem, you have to first determine the BPS spectrum, the full BPS spectrum. And the BPS spectrum is what gives you the Stokes lines of this Riemann-Hilbert problem. Are there other questions? Well, now I'm gonna consider a specific example, and hopefully I'll just keep that there, and hopefully this will become more clear as we go into the example. Right, so the simplest geometry that you can consider is, well, local P1 times P1, which is the total space of the canonical bundle over P1 times P1, and I will denote it by omega P1 times P1. And for this geometry, the quiver, well, there are many possible quivers, but the quiver that I will consider is this. And associated to, and what does this quiver mean? It just means I have a skew-symmetric pairing as part of my data. I fix a basis of my lattice, which will be gamma 1, gamma 2, gamma 3, gamma 4. So in this case of P1 times P1, the lattice has rank 4. H2 is just the two P1s. Then you have one generator of H0 because it is connected. And then you have one generator of H4. You pick a basis, positive integral basis of your lattice. And then you write the quiver in this basis. And what is this basis? Just to be precise, in terms of D-branes, this is called fractional brane basis, and gamma 1 is the D4 brane, gamma 2 is D2F anti-D4 brane, gamma 3 maybe I don't want to write it down, is some other combination, and then gamma 4 is anti-D2B D4, and here I just take in D2B is the D2 brane wrapping one of these P1s, and D2F is the D2 brane wrapping the other one of the two P1s. It means base and fiber, but we're not really using this. If you're more mathematically oriented, in terms of sheaves, gamma 1 would be just the line bundle omega 0, 0. Then you have omega 1, 0, omega 1, 1, and then omega 2, 1. So you have a concrete basis of sheaves over the space, or of D-branes over the space, and you write this quiver. What does the quiver mean? It just means that gamma I antisymmetric pairing with gamma J is an antisymmetric matrix. It's just the basis representation of this. And for example, if I have two arrows, in this case, this will be 0, 2, 0, minus 2, minus 2, 0, 2, 0, and so on. And the number of arrows from node I to node J is just this with sign. So if there are two arrows going from 1 to 2, here you have 2, and minus 2 arrows from 2 to 1 because they're incoming. So we have kind of a concrete quiver, concrete basis for the space. And we already have kind of a lot of our data. Yeah. So this approach, the approach that I'm gonna tell you about will determine everything that participates to wall crossing. Wall crossing is determined by the antisymmetric part of the quiver. So yeah, this is, for example, for the conifold, it won't work, but the conifold is kind of trivial, so we don't need this. Um, uh, the hard, the very hard thing is typically to determine everything that participates to wall crossing. So now we have this this basis, and we have to introduce a central charge for this. Now, if you have in mind the geometric engineering pictures, well, this or in general the gauge theory picture, the central charges will be integrals of a Seiberg-Witten differential over cycles of a curve. But for me, these are part of the initial data. It's always the case that when you have a Riemann-Hilbert problem, you're kind of inverting what you take as given as instead of what you want to what you originally you would compute. So in general, you could have some configuration of central charges. Let's say this. And this will lead you to a very nasty spectrum. In fact, you can classify what type of BPS spectrum you can have, and you can either have a chamber where you have a finite number of stable states. This is kind of the typical behavior of Argyres-Douglas theories, isolated, strongly coupled fixed points. But this will never happen in 5D, because you always at least will have Kaluza-Klein towers. So the spectrum will be infinite, or at least it is expected to always be infinite. But here it's infinite, it will be infinite in a very bad way, because you will have a certain number of hypermultiplets. So omega is equal to 1 means hypermultiplet, and then you will have, so let me just write it here. Omega is equal to 1 hyper, omega is equal to -2 vector. And inside here, you will have arbitrarily high spin states organized in like rigid trajectories. It will behave very, very badly. And here you won't be able to write any kind of closed formula for these. But what you can do is be a bit more clever and say, well, I can align these central charges. Now, in general, when you align central charges, what happens is that you're on a wall of marginal stability. Physically, this means that you don't know what is stable, what is unstable. You can't really understand what really is the spectrum of stable particles. But there's a catch here, because as long as you align central charges that have zero pairing in the quiver, so there are no arrows connecting 1 and 3, there are no arrows connecting 2 and 4, and if you align them, well, mathematically you could still say that you're on a wall of marginal stability depending on how you define a wall of marginal stability. But this issue doesn't present itself. So you will still be able to completely say what is stable and what is unstable. So how do we determine? So let's say that, okay, let's take a wild guess and think that if we align these spectrum things, if you align these central charges, things might go a bit smoother. And this wild guess was originally in a section of a paper by Clossier and Del Zotto from 2020. But now we have kind of a very general understanding of why this works and how this allows us to compute everything. So let's say that we start from this configuration. And here on the real axis, we have the central charge of the D0 brane. The D0 brane is always the sum of all the nodes for these quivers that I'm considering. So I want that the sum of everything is real, because in a physical normalization, we want this to be equal to 2 pi over r, the kk momentum. So I know that these kind of, because these appear as quiver nodes, they're stable states. So what are all the other stable states? Well, I picked this basis, but it's a choice, right? It's a very arbitrary choice what basis you pick for your lattice. So, and this choice also means is related to the fact that I'm picking a half plane. I'm focusing on the problem on this right half plane. And the reason why you can always focus on a half plane is that due to CPT, CPT sends gamma to minus gamma, inverts these charges. So Z gamma to minus Z gamma. And so if I determine all the stable states here, I will know them also. That I will know that also all their opposites will be there. So I have this choice of upper half plane, and what I can do is that I start rotating my axis. The upper half plane is completely arbitrary. I chose this right half plane, but I'll start rotating my axis. Well, this, yeah, looked like colored, but it wasn't. So I'll start rotating my axis. And at some point, I can, my axis that determines my upper half plane can cross my basis. So this is no longer a good basis, because it's outside of the upper half plane that I can choose. And well, I already know, because of what I just said, that here I will have Z of minus gamma 1, which is Z of minus gamma 3, because of CPT. But in fact, there's a general rule of what happens when this ray goes out of the upper half plane, and this is known as a cluster algebra mutation. So if I mutate on the ray K, this is, the change of basis is minus gamma j if K is equal to J, or gamma j plus the maximum between B, let me not get confused with signs, Kj and 0 times gamma K. So here I'm doing simultaneously a mutation at 1 and at 3, but actually they commute if you study this in detail, because there's 0 pairing between them. So what happens if I do this mu1 and mu3 is that my charges, the new charges that are the new basis, well, let's see, this is here, gamma 1 goes to gamma 2 minus gamma 1 plus gamma 2, which is just this, yes, minus gamma 1. Then gamma 2 goes to gamma 1 plus the same thing. and gamma 3 goes to this, and gamma 4 goes to this. And the quiver becomes almost the same. It's the same, but with, yeah, actually, 2 and 1 exchange and 4 and 3 exchange. So what we can, and we can repeat this procedure, and you see it's very regular. So what you will find is that at every step, you will get shifts by these same things. And if you include also the permutations so that at every step the quiver remains the same, yeah. What? Hmm. So this omega kind of measures the how the generate, like the dimension counted with the signs of your BPS Hilbert space. So this -2 comes from the 2 helicities of the gauge field, and the 1 comes because it's just a scalar. So you have 1. No, but here I'm not really, this index, it really only includes the, yeah, we're on the Coulomb branch. So this index really includes the Lorentz behavior. Then you can refine it, but yeah. Are there other questions? Well, what happens is that essentially by iterating this, you can find that your BPS spectrum is given by shifts of gamma 1 and gamma 2 by this vector here, and then the same thing with gamma 3 and gamma 4, but with the other vector. And all these have omega is equal to 1. Now, what happens is that what we still don't know. This is already a lot. It looks, it's almost all the states, but this is leaving undetermined what happens on the real axis. So now we have to remember another thing that was mentioned last week, that you have this generating function of refined DT invariant, motivic DT invariance, and this is invariant. And at some point, it was written last week that this is given by this phase-ordered product of quantum dilogarithms. The phase ordering, it's really necessary because now we're promoting everything to non-commuting variables when we write in this formula. So this generating function will be given by the product over all the rays. Let me write it correctly. So n greater than 0 and increasing. And here you have quantum dilogarithm, which is just a Kupo-Kammer symbol, basically, plus n gamma 1 plus gamma 2. And then you will have phi of x gamma 2, gamma 3 plus n gamma 3 plus gamma 4. And then you will have something that you don't know, that is on the real axis. I'm doing this. I'm writing a phase order product going clockwise, starting from the y-axis. So now this is the real axis, and then you will have the same thing here, but including the rays that are below, that are just the rays of these. But we could have done the same thing, the same identical computation, by just exchanging gamma 1 and gamma 3 with gamma 2 and gamma 4. So there will be another one which will be exactly the same, but with 1 exchange with 2, 3 exchange with 4. And these are equal because this thing is invariant. So you can solve this equation for the thing that's in the middle. And what you find is that in the middle, you have gamma 1 plus n times gamma 1 plus gamma 2 plus n times the d0 brane, gamma 3 plus gamma 4 plus n times the d0 brane. And these have omega is equal to -2. So you have not just towers of hypermultiplet, but you have the kk towers over the vector multiplets. And this is your whole BPS spectrum in this chamber. So this formula gives you kind of a closed form for the BPS spectrum of this geometry correspond to 5-dimensional SU2 super Young Mills in this chamber. But the thing is, it gives you also an exact formula as infinite product of this invariant thing. Yeah. Yeah, so as I said before, I was just about to get there. As I said before, this determines everything that participates to wall crossing. So the D0 is a flavor charge. So it cannot be determined by equating these two. It's kind of a prefactor that will be common to both. But actually, yes. One also needs n times gamma D0. These are also stables on the real axis, all the kk momenta, which are towers of skyscraper sheaves. And this, well, this was first rigorous. We kind of conjectured it in this paper, but it was rigorously derived by Yuri Zhang, which is a student of Tom Bridgeland in a recent paper. And in fact, this is kind of follows from, we have this paper with Bridgeland and Jovenzana that is about to appear, and there's a general proof of this for a lot of, a very wide class of 5D geometries. So just to tell you kind of why this is happening. So this is now understood. It's not a coincidence just because of this geometry. It comes from permutation symmetries of this quiver. So in this quiver here, you have this Z4 permutation symmetry, and we're finding a locus which is invariant under a Z2 subgroup that is not on a wall of marginal stability. So we have this. We have determined the BPS spectrum. Great. But this was our order 0 problem. So now we want to solve this BPS Riemann-Hilbert problem. And this is kind of an infinite dimensional version of a Riemann-Hilbert problem. Very, very hard in general. But we will reduce it to solving just a Q difference ordinary differential equation. How are we going to do that? So let's draw what is called a ray diagram, which is just the kind of set of Stokes lines for this Riemann-Hilbert problem. It looks like this. Marcus Marino would call it a peacock pattern. Probably a lot of other people would call it a peacock pattern. This is what the name of this kind of pattern typically is called, because it looks like a peacock tail. So you have these towers that are on a real line. And in fact, you can do a bit more than just that. Once you determine the BPS spectrum there, you can separate Z1 and Z3 a little bit, as long as nothing crossed, as there's no wall crossing. So here we take something like this. And you can show that where Z gamma 1 and Z gamma 3, so let's say that Z gamma 3 is equal to Z gamma 1 plus some real delta. Z gamma 2, gamma 4 is equal to Z gamma 2 minus the same delta, so that the sums are still on the real axis. Then there's no wall crossing. So let's look at that formula that I did not compute. What happens if we zoom in? We zoom in here. We're on this ray, the first ray, and we want to see what happens if I jump like this. Sorry, maybe yeah, it should have been like this. The orientation was wrong there. So now, if I jump, if I do a sequence of 2 jumps, okay, let me go a bit with order. So first, notice one thing, that if something is a flavor charge, it doesn't jump. So this means that in this case, we have that quiver, the matrix of that quiver has a 2-dimensional kernel, and I can define T in this way, and this will be just exponential of the central charge over epsilon. And the same thing will be true for the D0 brane, which I'm gonna call Q. And now I want to, normally I would induce this jump by changing epsilon, but I don't want to do that. Instead, I'm gonna, remember these central charges are part of my data. So instead I'm gonna vary continuously the central charges. And I'm gonna vary them in a way that if I define Z gamma 1 with an overline as the one shifted by this, so I'm going from this to this, and Z gamma 2, so it's the same thing that happened in that when I was rotating that upper half plane. So this goes here, and in general Z gamma of S, I define it to be 1 minus S Z gamma plus S Z gamma bar. So I'm continuously deforming these central charges like this. I'm fixing epsilon. And I'm assuming that the phase of epsilon is somewhere around here. So at some point, the phase of epsilon will cross the phase of an active ray, not because I'm changing the phase of epsilon, but because I'm changing the active rays. I'm just continuously deforming them. But still, it's gonna jump by definition of our Riemann-Hilbert problem. And it's gonna jump like that. So what happens to, first, let's see what happens to these two. Instead of using, to describe my X gamma, instead of using gamma 1, gamma 2, gamma 3, gamma 4, I'm gonna use, let's say, gamma 1 and gamma 2, and then these two. It's just a change of basis of my lattice. But because these change in a nicer way, what happens is that Q stays invariant, but T does not. T gets shifted by the zero brane. And you can see it from here. T is -2, -4. So the Z gamma 4 will transform like this. Anyway, let's not go too much into it. If you want a bit more detail, I'm here the whole week. But this is what happens. And then X gamma 1 bar, what is it? I just use the Kontsevich-Soibelman formula. And this is, let's call this gamma 1 plus gamma 2 V1 and the other one V2. It's this times 1 plus X gamma 3 over 1 plus X gamma 1 squared. And X bar of gamma 2 is X of minus gamma 1. And here I also included kind of this permutation of the nodes so that the quiver goes back to itself. So this is really the transformation under a discrete time evolution T, which is the sequence of the two mutations and a permutation of the nodes. This leaves the quiver invariant. But now this will be the solution of the same problem. I have the same lattice, the same quiver. It will just be a shifted one. So, and the shift is encoded in this T goes to Qt. So I can write this equation also noting that this X gamma 2 is, yeah, let's do it. So in general, I have X gamma bar is X gamma of Qt. And then this equation combining the two tells me that X gamma 1 of Qt, here I'm just doing some rearranging of these charge labels so that I write everything in terms of Q1. X gamma 1 of Qt times the same thing but with an inverse. What is it? It's X gamma 1 plus Qt over X gamma 1 plus 1 all squared. But this is magic because this is the Q-Panlevé 3-3 equation. And they're classified. They're given by, this would be given in some classification notation by some pair of affine root lattices. So what we find is that the X gamma for this, instead of saying I want to determine them from the parameters of some equation, I'm saying what are the transformation rules of these? And can I use these transformations just to solve them? And I find that this infinite dimensional Riemann-Hilbert problem, in this case, is equivalent to this Q-Panlevé equation. And here I have deformed this configuration of central charges a little bit. But what happens if I go back to my original one and I put gamma 1 on top of gamma 3, gamma 2 on top of gamma 4? Well, these two constraints tell me that x1, I won't write gamma, but it's kind of clear what I mean. And then I have x2, x4 is equal to t inverse. So if I set really that x1 is equal to x3 and x2 is equal to x4, I find just algebraically that I must have, for example, x2 is equal to x4 is equal to t to the minus 1/2. x1 is equal to x3 and is equal to q times t to the 1/2. And this is just exponential of some central charge over epsilon. But this is also the algebraic solution of this Cupan-Levy equation. It's the simplest solution that you can find for this Cupan-Levy equation. And in fact, it's yes, thank you, of course. Hmm? There might be some power wrong, but you get the gist of it. Right, so the very simple solution is the simplest one to the corresponding Cupan-Levy equation. And when I deform, what happens is that you immediately go to a one-parameter transcendental solution of Cupan-Levy. So now here, the BPS spectrum is the same, but the Stokes diagram is kind of doubled. And the solution to the equation becomes much, much more complicated. Good. And in fact, this is a kind of a general theorem from this last paper from, well, it's going to appear soon in 2020 in CMP, but this 2306, that every time that you have such a permutation symmetry of the quiver, you can find, you can, if you have a stability condition that is invariant permutation symmetry, and it doesn't lie on a wall of marginal stability, which means you're not aligning charges with non-zero pairing, you will have this trivial solution to the Riemann-Hilbert problem, which was kind of very unexpected because it's a very complicated problem. And this is not a singular locus, really. So if you look at things like the mirror curve, it's still genus 1. There's no degeneration. But you can solve it exactly. And then you perform it, but it allows you to find also the equation a bit outside of that region. And also, fortunately for us, a very beautiful paper by Bernstein and Shechkin. It's from, well, 2021. I don't remember the archive number, but you can easily find it. Classified these algebraic solutions for Cupan-Levy equations using what are called folding transformations. So algebraic solutions are those invariant under foldings of a corresponding rational elliptic surface. So we have all the we go through the list of algebraic solution by Bernstein and Shechkin. We find those that do not lie on a wall of marginal stability, and we win. This is all, it tells you kind of complete description of BPS spectra, exact solution of these, and maybe I would like to quickly turn on I just want to show something very quickly. Okay, I'll keep talking while it warms up. Yeah, so good. And the thing is that if you look at the classification of these Cupan-Levy equations, this case that I just described is this A1 affine. There's only one, these discrete shifts are affine translation on these root lattices. And there's only one translation on A1 affine, but the other cases have more. So there are many flows, they correspond to different chambers. And if you start with a solution with respect to one flow, the other ones act as an infinite dimensional group of symmetries. They act as Backlund transformation of the integrable system. This is their name. And so if I start from this trivial solution, which is exact, I can find very non-trivial solutions, which are also exact, by applying this Backlund transformation. So this is an example for, this is SU2 and F equals to 4, local del Pezzo 5. And what happens is that it will still be given exactly by this exponential of central charge over, well, this h bar is epsilon. but it will be a rational function of these exponentials in a very non-trivial way. So this gives you an infinite number of exact solutions to this Riemann-Hilbert problem. And this is, when you deform it, the solution will be given by ratios of dual Nekrasov partition function. This is something called the Kiev formula. So there's a very nice picture that is emerging. If you have a 5D theory, look for these regions in the moduli space that are invariant under these symmetries. And this will give you the exact BPS spectrum. This would be part of a theorem that we're working right now with Bridgeland and Jovensana. It will be out hopefully very, very soon. And this determines all the Stokes rays. Because you're in these nice chambers, you will be able to write the Riemann-Hilbert problem as a Cupan-Levy equation or a generalization of Cupan-Levy equations. And then you're reducing this to solving Cupan-Levy equation. You have this complete invariant that you can write down, and you can also go to other chambers if you want. That will be non-trivial, but you still will be able to say quite a bit. All right, I think I'll stop here. Yeah, yeah. Mm-hmm.
Are these two necessary? I mean, is it really necessary? You just go to you don't need. It looks like you don't need to combine the local ones and just go to special locals where you're the symmetric and the same argument applies. Do you need to combine number one and number three in the discussion?
So if I just cared about computing the BPS spectrum, then I could put them. I could go to this case where they're non-aligned, and all the discussion would be the same. But as soon as, for example, if I deform them in a different way, then I might open up this cone, and then I can't say what's inside. So the crucial thing for the correspondence with Cupan-Levy equation is that the whole Riemann-Hilbert problem is invariant under the affine translation, and then you can compare the things before and after. Yeah, yeah. So are you thinking about more general geometries or different quivers for these same geometries? Okay. So for more general geometries, if you write down a quiver, you can just write a quick Mathematica program to find this permutation symmetry group. And then you can immediately check if there's a subgroup of this permutation symmetry group that is whose invariant locus is not on a wall of marginal stability. And another thing that you can do is, even if this lies on a wall of marginal stability, you can say, okay, this is bad, but I can try to open a little bit, just like I did in this way. And so, for example, in this, yeah, absolutely. Um, hmm. No. So for this discussion, it's at the point. So I should say that this is a very recent story, and there's so many things to investigate still. There's a lot of very interesting conceptual points that are emerging. And for now, the statement of, okay, also these span-level equations are solved exactly by Kiev formula type, so dual Nekrasov partition function, Q deformed conformal blocks. This is kind of a useful result to write these solutions explicitly. What happens is something a bit curious. There's probably something more deep going on here, because the Kiev formula you would have, I mean, um, so the let's look at what is this Q. So this Q that I wrote here is exp of z d0 over epsilon. So this is e to the, if you think of it in terms of a part of the story that I didn't discuss today, the WKB approximation for Q difference equation, this would be this in terms of the H bar of the Q difference equation. So you would have the monodromy for a Q difference equation, but the Q difference equation is with respect to this e to the H bar. And then you have the Q-Pan-Levé equation that's describing the monodromies of this Q difference equation, which is kind of a Langlands dual value of H bar. And I think that the Nekrasov functions would be written in terms of this Q. But I might, no. I might be, no, sorry. I'm just mixing two things. So this is separate. At the level of, no, okay, at the level of Nekrasov functions, it's really just a kind of a useful result from the literature at this point. I don't understand it. I don't understand the relation between the two. Yeah, this is related part of the story, but let's just mix in two things. Sorry. The x gamma. So the thing, for example, epsilon here appears everywhere. So, but it's always the same. I'm not changing epsilon. So I'm changing the moduli so that these rays cross epsilon. No, it's always the same because, for example, so this here, this x gamma will be in general functions of these 4 central charges and epsilon, but actually just 4 of these parameters. Okay.
Explicitly on the other side. You have one epsilon minus appearing explicitly, and then last prime.
Yeah. Yeah. So because this is kind of the usual picture where you're varying epsilon, but the only important thing is that you have an active ray that crosses the phase of epsilon. So I'm changing the active rays. And so in this case, if you want, it would be more like a, okay. Ah. So the input is these jump properties. This jump appears when you have the phase of epsilon is crossing, you have one of these active rays that is crossing the phase of epsilon. Yeah. So, yes. So everything here is epsilon minus. So this is comparing what happens before this crossing and after this crossing. And here I was denoting epsilon. So epsilon plus, epsilon minus just means before and after the crossing in this case. So yeah, it's a bit, this is standard notation. In this case, it's probably a bit misleading because I'm actually varying the z's, keeping the epsilon fixed. Okay. Uh, yeah. Yeah, finding x's that jump in this way. And for this trivial solution, for these x1, x2, x3, x4, there is no jump. In fact, if you plug these trivial values of x's in this formula, you see that there is no jump. But in the general case, you will find that these jumps are equivalent to the Q-Panlevé for this chamber. So in usual Riemann-Hilbert problem is you have an unknown function that jumps in some prescribed way, and normally it's a linear Riemann-Hilbert problem, so it's just matrix multiplication. In this case, I have some nonlinear function that jumps in this complicated way, and I want to see if this is enough to constrain everything. Yeah. So for del pezzo 3 and del pezzo 5, there these symmetric subspaces, this symmetric region exist, and you can write everything in the same manner. If you look at the for this upper part is 6, 7, 8. It's not clear. So this would be del pezzo 6, 7, and 8. Yeah, so for del pezzo 4, 2, and 1, these symmetric regions do not exist. You can see that the quiver doesn't have enough permutation symmetry. But what you can do, and this idea I do in this last paper, is you implement a decoupling procedure that brings you from, let's say, del pezzo 5 to 4, 3 to 1, and so on. And in these cases, you take a limit on the central charges. Physically, it's just a decoupling of a mass. Yeah, yeah. And it brings you to a new stability condition. You can see immediately that is not particularly symmetric. But if you take the coupling limit on the BPS spectrum and you compare it with the one that the BPS spectrum that you would compute following the procedure that I described at the beginning, they're the same. So you can, the idea is, sure, not all local Calabi-Yau threefolds will have these symmetries, but let's say that you can embed them into something bigger that does, and then you should be able to go down. Yeah, well, from this point of view, is there's nothing special about high rank. Actually, yeah, it's more or less solved. It's gonna appear soon. Hopefully, like it should appear soon. Mm-hmm. Mm. Uh, well, I tried to look into this high rank, maybe not hard enough, but if you just look at the list of algebraic solutions, they're present in this list by Bernstein and Shechkin, and they correspond to walls of marginal stability as far as I can remember. So it might be that you are able to say a lot in those cases, but not this complete picture. Yeah. Thank you.